Okay. Hello, everybody. Welcome. I think people are still coming in a little bit, but it's time to start with our webinar. Thank you all for joining our webinar, previewing a topic that we will also cover at our Thermal Management and Ceramics Expo conference in Novi, Michigan, coming up April 30 and May 1. The topic is data center cooling and making data centers sustainable with thermal management and ceramics innovation. My name is Peter Verkooyen. I'm the conference producer for the Thermal Management and Ceramics Expos. The conference will cover many topics and industries from post-silicon semiconductor materials and 3D printing with bioceramics to integrated thermal management in EVs and solving the thermal bottlenecks in electric aviation. Today's webinar will take only 1 hour. We have a packed program with 4 presentations followed by discussion and a chance for you to ask your questions of our speakers. The first up is Matt Greggs, co-founder and CTO at Deep Green, an immersion cooling startup focused on reusing waste heat from data centers. I think I may have that wrong, but Matt can correct me later on. He will be followed by 2 immersion cooling veterans, Herb Zien, a former CEO and now vice chair of Liquid Cool Solutions, and Serge Conesa, founder and CEO of Immersion 4. And finally, we have Yulin Wang, senior technology analyst at ID TechX, who will lead the discussion and Q&A after the presentations. So if you have questions for our speakers, please post them via the Q&A widget at the bottom of your screen. If you go with your cursor to the bottom of your screen, you see Q&A. That's where you can leave your questions for the speakers. And with that, I want to give the floor to our first speaker, Matt Greggs, co-founder and CTO of Deep Green. Ready? Take it from there, Matt.
Sure thing. Nice to meet everyone. Thanks for the brief introduction. We are, as I mentioned, we're building data centers. We are actually cooling technology agnostic, but I think the message you'll come from me here is that one of the main advantages from us as an operator's perspective of direct liquid cooling and immersion cooling technologies is the usability of the heat and the efficiency of its use. So brief introduction of what we do. We build data centers designed completely around heat recovery. The goal of this is to minimize the net energy impacts of the data center on its local environment and its local community, so that energy that is being used by the IT workloads is being reused in the form of heat. So that is being provided to public pools, heat networks to deliver material social impact where that's being delivered, at the same time as significantly reducing the operating costs and the costs to the end users of our data centers. The way we do it is very simple. We use a liquid-to-liquid cooling system across everything. We then use a very large thermal store and draw that off into the various different heat use cases throughout the environment. This diagram here is an example of a pool integration. It's very simple. We have no other ancillary systems that use heat. But the approach taken is very simple. We are looking to provide heat to the point of use at the optimal temperature for their use and give them as much of the heat as possible to reduce our cooling CapEx and OpEx costs. So we're backed by Octopus Energy. I'll drop straight over that. That's money. But they're a valuable partner to us, and this is fundamentally an energy play. And getting involved here, we're bringing the heat to where it's needed by moving those mobile IT workloads. Now, this is where immersion and DLC it really starts being key to our model. And that's the density that can be achieved by utilizing and fully embracing these technologies in your white space. This is enabling us to deploy very high dense modular and internal white spaces all over the country and map cooling solutions to available power and heat uses without being restricted by the normal problems you would face in air-to-air cooling systems in terms of the sheer size of the systems needed. On top of that, the energy efficiency from a PUE perspective is, I think, well borne out now, but that's something we really look to embrace within our data centers. And that's meaning that as a business, we're very excited when we see things like NVIDIA's announcement a few weeks ago and the developments in the HPC server manufacturing space around density of power on a per U basis. And it's really, in my mind, embracing these technologies now is key to having a viable data center in 10 years' time, rather than just a shed that needs almost the same amount of money as building a new one to be put into it to bring it up to standard. We're looking to build 300 megawatts across the UK over the next 5 years. That's across a mixture of pools, everything else, and then move on to developing a global network of these carbon neutral edge data centers that embrace this technology and meet all sorts of heat demands, and take that projected 10% of global energy usage in the data center space by 2030, and really take that down as low as possible in terms of our net consumption. So use our growth and the spectacular growth in the industry to solve another problem in the environmental space around electrification of heat. This is an example of this is London. These are just a few of the sites we have in development across London, and it's building out that mesh of DCs, and some of them may be very, very small, single, multiple immersion tanks, or 5 to 10 racks of DLC, facilitating inference at the edge and supporting a number of other compute heavy applications as those are rolled out. And some of them are much larger, more traditional centers. But I think where the journey we've been on with our clients at the moment over the last couple of years comes back to that density and economy of space. Now, we worked with a CSP where we've taken their 2-rack hypervisor, and with the help of some of our partners, we've gotten the next generation of that down to a 4U setup in immersion cooling. And obviously the savings for them, both from an energy efficiency perspective and energy utilization perspective, but also from a cost perspective, because the amount of floor print they're using up within the data center has been a real game changer there. So we're very focused on HPC and dense workloads over 10 kilowatts a rack, and we're seeing more and more demand going far over 50, and even into 100, 120 as we're seeing from NVIDIA. So that's not viable in air. You have to embrace these technologies. And our perspective, definitely, there is the right use case for immersion. There's the right use cases for DLC. There's the right use cases for precision immersion. It's very dependent on who you're working with as the best option, but we're really focused on designing to accommodate all of them in any given location to give the client the optionality they need. This is kind of our value proposition. It's truly diverse data center tech that looks and feels exactly like any other data center you're going to. We're embracing carbon neutrality. That is tracking all the embodied carbon, scope 1 through 3, as well as starting to look at scope 4, demonstrating the social value of what we're doing. So we're giving that heat away for free. That means in a pool and in a heat network perspective, that is directly reducing the bills to attend. And the efficiency that we can get from these technologies means we're able to compete very aggressively on price and target areas where there is limited power available, either by being very focused and very dense, or by running off or looking to develop sites that are almost off-grid in terms of the use of renewables and battery storage. And then this is us. I said any questions at the end, but really core to us is every prototype we've looked at, from the first which we ever did back in 2016, which was a crypto miner in a bucket of oil, through to now deploying technologies of like the ones you'll see later. It's been key to the value proposition and something we've seen as core to the way we're growing now and continuing to do so, embracing all of these technologies. I think I'll leave it there. I'll hand you over to Herb to talk a bit more about the detail of how this all works.
Thank you, Matt. Let me share my screen. I'm Herb Zine. I'm Vice Chair of Liquid Cooled Solutions. I'm a thermal engineer by education and experience. Let me bring this up, sorry. I'm anxious to discuss our technology with you. And if you're going to be in Michigan on May 1st, I'll be there and look forward to meeting you in person. In any event, people think of immersion as tanks for whatever reason, but there's rack immersion as well. And we'll discuss chassis-based immersion with forced convection. Of course, data centers are an environmental catastrophe. 200 terawatt hours of electrical energy in 2020, which is 100 million tons of CO2. Half the energy is wasted. Data centers consumed 660 billion liters of water in 2020. Almost all this water was wasted. And the solution, as you'll see, is our single phase immersion cooling based on racks, which slashes the carbon footprint, slashes the space requirements, slashes the infrastructure CapEx, slashes energy consumption, slashes maintenance expense, eliminates water consumption, and increases hardware life. Immersion, we believe, as a thermal engineer, I believe, is the end game for cooling electronics. Frankly, blowing hot air, blowing cold air, a hot thing in the middle of the room really never made sense from a thermal point of view. Liquid cooling is now getting traction principally because the chips are getting too hot for air. It can't do the job anymore. So as inefficient it was, that didn't seem to matter to many people, but now it can't do it. So liquid cooling is coming into its own, and there's several different flavors. We believe the end game will be immersion because it's the least CapEx, the lowest capital expense, and also the most energy efficient. And we believe that to cool a hot chips, you also need some kind of targeted forced convection. So with our technology, the electronics are isolated from polluted air, as with all immersion. Air conditioning, humidity control are not required, which is true of all immersion. No water is consumed. Data centers run silently. Servers last longer. The heat transfer fluid we use is commonly used by the electric utility industry to cool high voltage transformers and has been used for decades. It's safe. It has a global warming potential of 0, and it literally lasts indefinitely, forever. Here's where we part company with the tank folks. Higher server density per rack reduces the white space up to 70%. Tanks take floor space because they're a horizontal solution in a vertical world. Our enclosures fit in standard racks. By way of example, we can fit 18 2U servers in a 42U rack that the customer already probably owns. And 95% of the waste heat from servers can be recaptured and reused at 60C or 140F. So we can actually recapture heat as an edge. We offer, in fact, what we call a smart water heater, which is a zero carbon edge computing system that takes a 40 kilowatt rack and converts all that heat into hot water, 60C. This is what a server looks like, a 2U version. This is the front and the back. It's, as I mentioned, sits in a standard rack. Here's how it works. Everything is immersed. All the components are immersed, including the processors and all the boards and everything else. But on top of the processors, we basically install a submerged cold plate. And we target the heat using a small pump. It's about a 20-watt pump that circulates the liquid in the server chassis to the cold plate and then back into the liquid in the chassis for transfer at a liquid-to-liquid heat exchanger. Almost every data center either is planning to or will have to convert to add a liquid coolant loop inside the data center to serve those racks which are liquid cooled. And so what we do is we transfer the energy, the heat from the server to that liquid cooling loop in a liquid to liquid heat exchanger. We can get up to 72 kilowatts in a standard 42U rack. 100% of the heat generated is removed by the oil, and the remaining components are cooled by bulk flow after the high power components are cooled with this cold plate configuration I just mentioned. And there are no chassis fans, of course, or no fans anywhere. We replace them with high reliability, low power variable speed pumps. I mentioned that the servers last longer. So we did the company's located in Minnesota, which is a climate that gets very cold in the winter and very warm in the summer. And so we put a rack of our chassis running at 100% CPU load on the back dock of our facility there. And this is what one server looked like after 3 years of use with 100% CPU load. And as you can see, everything looks brand new. I mean, the reason you'd replace a server is not because of oxidation or corrosion due to air. You'd replace it because of technological obsolescence. Here's what a rack looks like. From the standpoint of the owner of the data center and the contractor building it, there's only 2 connections to make at the top or the bottom to the facility coolant loop. Everything else is done in the rack. Here's what a data center looks like. There's no chillers, there's no air handling systems, there's no water treatment systems. All you have, the only moving parts in the whole data center are the pumps to move the facility coolant around, and the fan in the dry cooler, typically. If it's cooler than 45°C outside, we can simply blow the heat away. Or, as I mentioned, we can recapture it at 60°C in a water heater. And what's interesting about, and of course, each server chassis has a small pump for the purpose of targeting those hot processes. Installation. Installation is similar to air-cooled units. The racks can be pre-configured with the cooling loop components prior to placement in the facility. They can be retrofitted or alternatively with a manifold for connecting the heats. So they can be either pre-configured or retrofitted. It takes about 4 or 5 hours to convert a rack from pure air to a combination of air and liquid. Servers and heat exchangers are placed in the racks in clusters of 6 in our case, it could be any number, and filled with a dielectric heat transfer fluid, typically in the rack. It takes about 5 minutes to do that. Connections to power fiber in the facility loop are then made, and each rack has only 2 connection points, as I mentioned, to the facility primary coolant loop. And then maintenance, 2U server weighs about 32 kilograms, which includes about 20 liters of oil. And you can drain it in situ, right in the rack. And we have a fill pump station that basically pumps out the liquid into a reservoir for reinsertion after the maintenance is done. And it takes about 4 minutes. The fluid does not degrade, and components are protected from oxidation and corrosion. If a server requires maintenance, the server is powered down like an air-cooled server would be. You simply disconnect the dripless quick disconnects for the fluid loops. There's 2 on each server, an inlet and an outlet. The chassis is pumped out, and then the server can be removed from the rack. It weighs about 15 kilowatts empty, mostly electronics. One of the great things we think about tanks versus racks, one of the great things about racks is that you can migrate so easily. You can simply migrate from air to liquid during the normal refresh cycle, and it actually costs less. When it comes time to refresh, instead of buying 4 air-cooled servers, you can buy 1 liquid-cooled server, LCS cooled server, and it costs less actually. So that is our story. For those of you in Michigan, We'll be in Michigan on May 1st. I look forward to meeting you. And now I'd like to introduce Serge.
Thank you, Herb. So very nice meeting you, everyone. I think we all agreed on the air cool is definitely not the path that the future of data centers are going to be taken. And I think we just need to. Oh, I'm sorry, I didn't share my screen. Sorry about it. And the reason why is very simply said, because the air is an insulator, where the liquid is a thermal conductor. If I will make an analogy, and I'm pretty sure that all of us will agree on that, imagine that this is a cup of champagne, and you want to cool the champagne. So what do? Are you going to cool the entire room, or are you going to cool the champagne itself? Well, basically, if you cool the entire room, it's a data center with an air circulation in order to be sure the hotspot is going to be as cool as it should be. Or if you cool the champagne itself, that's immersion flow. So basically what you see on the screen is what we call the DTM system. DTM system because the thermal regulation and the full management of the liquid is fully integrated. So we have designed this product based on the very simple matter. How can we welcome all the legacy of electronics, 1U, 2U, 4U, 8U, 14Us, no matter its destination, servers, routers, and welcoming up ourselves on board with all the patch panel, all the internet distributions, as well as the electrical distributions. That's the way, we design our system. We can welcome absolutely any brand within the chassis that you can see here on the floor. And when you look on the side, what becomes a data center that we know today? Well, basically a data center for us is a 2.7 meter high, 1.2 tons on the floor, and on the 270 square meters, we can basically pack up 3.6 megawatts of IT. So basically, when you look today, what is the company? The company has been created in 2017. We have the capabilities to do the entire R&D and the entire manufacturing. The main goals has been to have 4 principles and 4 pillars. The 4 pillars being to be no CO2, no greenhouse, no water consumption, as well as to be ethical. And ethical for us was eco-conservation. The best, energy you save is the one you don't use. Environmental conservation, because we need to take care of the environment, ecology, and of course, economy, with an ROI inferior, less than 1 year, and a TCO up to 90%. With an increase, things is on the decommissioning cost. What is the difference between an air-cooled data center versus an immersive cooling data center? Well, you don't have raise flow, high ceiling, chemical fire suppression, crash, right, the entire cooling infrastructure. You basically have 4 walls and a roof. And you're able, within almost any building, based on the fact that you have 1.2 tons on the floor and 2.7 meters high, build the data centers. So we change completely the perspective of designing a data center with this upfront scaling, with this upfront capex, to be put on the table. And at the same time, we give the benefit of no pollution and no water consumptions. So based on that, we were also looking at what is the tendency of the market, what are the applications that we have when we are talking about AI, machine learning, deep learning, data mining, as well as server applications. Everyone is servers. At the very beginning, when we're talking about 5 years ago, GPUs were the hotspot, CPUs, GPUs were the hotspot. Today, everything is heat sensitive. There is memory, ASIC, FPGAs, hard drive. Everything needs to be cooled. Plus, there is another issue that no one is speaking, which is the elephant in the room, which is the e-waste, which is generated by all these electronics. Because today, sadly, we only recycle 17% of the electronics. So we decided to design our DTM system based on a way to be sure that those products will last longer with 100% biodegradable liquid and 100% recyclable. And we guarantee the liquid 25 years. So based on that, we say, well, let's don't sell the product. Let's rent it. And Immersion 4 is only focusing on renting the solution from the 36 months contract to a 10 years contract. what is the specificity of the company? Specificity of the company is basically everything from R&D to the food production, okay, is done in-house. And we do not want to use any natural resources. And I will say no pollution emission. And by this, we want to be sure that the maximum of the energy coming, I will say, within to the data center is going to be used to power the IT load, not to power the cooling of the data center itself. So that's what Immersion 4 is all about. Thank you so much for your attention. I hope I was feeling on the 7 minutes we had, and I'm very happy to answer to your questions. Yulin, your turn.
Yeah, great, thank you. I'll quickly share my screen. Oh, you have to stop sharing before I'm allowed to share.
Whoops, sorry.
Oh yeah, great, thank you. I am assuming that you can see my screen. Yeah, great, thank you. So hello everyone, my name is Yulin Wang and I work as a senior technology analyst at ID TechX. So today my presentation will be about liquid cooling trends for data centers. So this is the agenda for my presentation today. So initially I will talk a little bit about the cold plate cooling, which is also known as direct-to-chip cooling. And then we will delve into immersion cooling, which has been mentioned and heavily discussed already. And then I will talk a little bit about thermal interface materials, which is relevant to ceramics. So that also echoes back with the, the topic of the conference. And then finally, I will wrap up by giving some market insights and summary and, like my opinions on how this industry is moving forward. So all of everything that I'll be talking today is essentially from my research report on thermal management for data centers. So if you are interested, please do feel free to click this website and then check out online. There are also some sample pages available for free downloading. So please do have a look. So having said that, so we'll talk about the cold plate cooling as our first topic. I'm pretty sure a lot of you are already familiar with cold plate cooling, but for those who don't know much about it, this is just a very brief introduction. So essentially you have a server rack here, and within the server rack, you have multiple server boards. So what happens with the cold plate is that within each server board, you have a limited number of heat sources. So for example, GPUs or CPUs. So those are the main heat sources. However, as mentioned by Stuart just now, there are also like a lot of other heat sources. For example, like memory modules. However, when it comes to cold plate cooling, we don't really care too much about those like small heat sources. We primarily focus on GPU, CPUs, chipsets. And the principle of it is pretty straightforward. So if we take a look a bit more closely, so this is the heat source. Essentially, the cold plate is mounted directly on top of the heat source with a very thin layer of thermal interface materials somewhere in the middle. And the cold water flows in, and then it circulates within the cold plate, and then thanks to the convection, the cold water gets heated up, and then the hot water flows out and then flows back to the condenser, the heat rejection unit. So this is the entire circulation. So the unique value proposition of cold plate from our research usually lies on the internal chamber design. So like how to make sure the chamber can maximize the heat dissipation of the cold plate. So that is usually the unique differentiation across different cold plates providers. So this slide sort of like shows the single and two-phase cold plate comparison by different parameters. So first of all, in terms of the fluid status, so for single-phase cold plate, the liquid always stays with a liquid and there's no phase change, whereas for two-phase cold plate or two-phase evaporator, there's phase change happening. So the liquid flows in and then it gets heated up, something like this, and then the vapor flows out and then flows back to the condenser where it gets condensed back into the liquid and then flows through the evaporator again. So this is sort of like a self-regulated system. In terms of the important parameters for single phase and two phase, so for single phase, the important parameters include pressure drop, and of course the inlet and outlet temperatures, as in the delta T, between the cold water and the hot water. Whereas for two-phase cold plate, the boiling temperature of the coolant is equal to the vapor outlet temperature, and also it's pretty important to select the right boiling temperature, because otherwise you won't be able to make it work as efficiently as you want it to be. In terms of the commonly used coolant, so for single phase, water glycol is pretty commonly used, whereas for two-phase cold plate, is usually based off the dielectric coolant. So one thing that is worth noting here is that the fundamental working principle is very different for single phase and two phase. Because two phase is using dielectric coolant, which are pretty usually bad in thermal conductance. So the way that it absorbs heat is by the phase change, by the latent heat during the phase change, rather than the convection, which is the method that single phase cold plate primarily relies on. So regarding the pros and cons, so for a single phase, because it's just water glycol, there's no environmental risks, and the cost is relatively lower compared with two phase. So the single phase cold plate is already very widely adopted. It's a relatively simple technology, simple design as well. And however, in terms of the downside, because of the water glycol, the nature of the liquid, there might be some chlorine issues and the bacterial growth, which ultimately leads to a relatively high maintenance over time. And in terms of the pros and cons for two-phase two-phase evaporator, some dielectric coolant have the global warming potential, and there might be some PFAS regulations being enforced. Additionally, higher cost and limited providers of the dielectric coolant also becomes a potential barrier in the future. However, the benefits of two-phase coolant or two-phase cold plate is that the coolant is, because it's dielectric coolant, it's usually chlorine-free, which leads to a low maintenance or free of maintenance potentially over a very long time. So this maintenance issue then leads to our next analysis, which is the selection of the rack manifold materials. Because of the potential chlorine, the rack manifold material for single-phase cold plate is primarily just stainless steel, whereas for two-phase, because it's chlorine-free, so you have a wider selection of the manifold materials. So you can choose from stainless steel, copper, aluminum, and some various forms of plastics for your decoupling connection part. So those two are the simple kinematics of single phase and two phase. So yeah, at the moment, single phase is pretty much dominating the entire market, or the entire like a cold plate cooling market. However, we do believe that two phase presents its own technology advantages and potential opportunities in the future. And then we will jump into the immersion cooling. So for immersion cooling, we have been talking about immersion cooling, but primarily we refer to single phase immersion cooling, which is the one you can see on the left-hand side. And I won't go into too many details about it because the previous speakers have given a really good overview of single phase immersion cooling, and we'll just jump to the two-phase immersion cooling straight. So essentially, two-phase immersion cooling utilizes is sort of like a latent heat during the phase change to absorb the thermal energy from the heat source. And then the vapor flows to the condenser, which is nothing but just a bundle of copper tubes. So at the condenser, the hot vapor gets condensed, and then the condensed liquid flows back into the tank. So this is the entire working principle. So I happen to see some questions in the chat, and so this slide hopefully answers some of the questions. So this is the roadmap and market opportunities for single and two-phase immersion coolant. So in terms of the single phase, the typical coolant is the hydrocarbon, whereas for two phase, it's usually fluorocarbon. And the fluid loss for single phase is usually very limited, whereas for two phase, it can be potentially very large, because during the vaporization process, the vapor, it is like easier for the vapor to escape from the tank, which ultimately leads to a loss of the fluid. So this is also why when it comes to, if you really talk with two-phase immersion cooling solution providers, many of them would stress the importance of a good sealing in their systems. Regarding the toxicity, so single-phase coolant has no toxicity usually, whereas two-phase immersion coolant, some of them have toxicities. So regarding the cost, so both single-phase and two-phase immersion cooling, the cost pretty high. Well, the costs might be slightly higher for the two-phase immersion cooling. However, it really is subject to, like what sort of coolant you're using and the maintenance cost. So it's pretty hard to, evaluate which one is more cost effective over the long period of time, because the total cost of ownership could vary depending on many factors. So regarding the biodegradability, so single-phase immersion coolant are usually biodegradable, whereas for two-phase immersion coolant, some of them are forever chemicals. That's why they are really susceptible to the PFAS regulations, and many of them are not biodegradable at all. Regarding the maintenance, single-phase has low to medium maintenance. One thing that is worth noting is that this also largely depends on what sort of like a liquid you're using. So for example, if you're using mineral oil, then the purity of the mineral oil is typically pretty low. So if you use mineral oil, then the longevity of the oil might be less than 5 years. As an example, of course, it's also subject to many other factors. Whereas in terms of the two-phase immersion coolant, the maintenance could be medium. One of the biggest barrier essentially is the sealing, and also when you change the servers, how to minimize the loss of the liquid. And finally, we come down to the cooling capacity. Compared with cold plate cooling, both single-phase and two-phase immersion have pretty high cooling capacity. However, two-phase immersion cooling typically has a higher cooling capacity compared with their single-phase counterpart. And finally, I will briefly touch on the thermal interface materials and how different thermal interface materials are used with the transition from air cooling to liquid cooling or even to immersion cooling. So thermal interface materials come with different forms. So we have the gap pads, we have gap fillers, adhesives, phase change materials, and thermal grades. So there are several key trends, which I have already listed here. So with the ever increasing, TDP, thermal design power of the GPUs, we do believe that high performance thermal interface materials are increasingly needed. So essentially, this means thermal interface materials with a higher thermal conductivity will be increasingly needed for the data center applications. And in terms of the considerations for the selection of thermal interface materials, thermal conductivity, of course, is very important. The material compatibility. So especially if you want to use immersion cooling, the team compatibility with the coolant plays an important role. As far as I know, some thermal grades might degrade or even dissolve in some sort of like a coolant, and then it will contaminate the entire tank, which will lead to some pretty bad results. And also the stiffness or the softness of the of the team. And finally, the cost of the team also plays an important role, especially if you're talking about large-scale deployment. One very interesting sort of team is graphite. It has demonstrated a pretty high thermal conductivity, both in plane and through plane, and it potentially offers some pretty good commercial opportunities for the data center applications, even for immersion cooling scenarios. And finally, I will quickly wrap up my presentation with 4 important key takeaways. The first one is liquid cooling. So we do believe liquid cooling will experience a very fast increase. So this has been sort of validated already by NVIDIA. So NVIDIA, I think several weeks ago, they released their Grace Blackwell chip, and they also sort of like mentioned that they will use liquid cooled server rack. So liquid cooled will definitely be dominant in the future. And we do believe that direct to chip will take off as the first step, and then eventually we will transition to immersion. So this sort of brings to our second conclusion: air plus cold plate cooling dominates in the near future, and immersion cooling gets popular with large companies start pilot projects. And finally, with our analysis, we do believe that there is a very significant market opportunities. So from our investigations, the liquid cooling hardware yearly revenue will exceed $900 million in around 10 years of time. So again, all of these points and key takeaways are from our research in thermal management for data centers. So if you are interested, please do feel free to click the link and check it out. Yeah, so that's my presentation. And I will stop share. Oh yeah, so I do see a lot of questions in the chat. Yeah, so now we will transition to the Q&A session. And while we're answering those questions, please do feel free to continue submitting your questions, and we will go through those questions one by one. So yeah, one of the questions is, what is the cooling liquid used? Can you share the general specifications? I think I sort of touched on this already, but I will just open these questions to the entire floor. So what are sort of like a coolant specifications for immersion cooling you can think of?
Let me address this. The fluid we use currently is what they call a polyalpha olefin oil. It's a product that's generic. It's been around for decades, principally to cool high voltage transformers and substations by electric utilities. It's inexpensive. It has a very long life. And mineral oils we've tested, and frankly, as mentioned, the impurities, they have a short life, and they muck up, frankly, the piping. We find we've had great success with the PAO oils. Now, some companies that manufacture, and it's commonly available by Shell, BP, Castrol. A lot of suppliers make this chemical. There are some companies now introducing a bioengineered version of it because it's basically a synthetic hydrocarbon, and we'll see how that goes. But our success at the moment with PAO oil is pretty impressive.
Thank you. Serge?
Yeah, well, the liquid on our side, okay, we decided to do our own liquid. So it's a PAO. Okay, we move away from any kind of mineral oil because we find ourselves, like I said, Earth was mentioning, I was at a short lifespan and so many issues. And the main characteristic of our product is based on the fact that we are on, I would say, on a temperature range on a -60 plus 250. And we are absolutely stable on the molecular standpoint. That means that we do not have, any issue, no matter, the kind of the materials compatibilities or anything that we're immersing inside. Another thing which is also quite important is to be sure that, when we speak about fiber optics, okay, we have the reflective index under control in order to be sure that we can connect from 1 gig to 400 gig, optical interface, which is our case. And we decided to do our own liquid because we wanted to be able to control what in fact is going to be the compliance with, I would say, any materials that we're going to be immersing, and what will be also, the fiber optics, I would say, reflective index, in order to be sure that we can effectively do what we want to do. That's the reason why within immersion 4 we're immersing absolutely everything.
Great, thank you, Serge. All right, yeah. I think we'll move to the next question. So there's another question for you, Serge. So how do you see the application and market for immersion 4 tech in the telecom industry?
Oh, we said telecom industry is one of them. The fact that we are, I would say, feeding, any kind of connectivity and any kind of device. Even I would say we did a test, I would say, for 3 years with one of the biggest router in the planet, the Nokia 7750. Okay, and basically everything works absolutely great on every single level. Telecom industry is we're talking basically about gigs, about, I would say, interaction centers, as well as all the routers that we can find, and all the kind of switches from Cisco, so on and so forth. And I do believe the telecommunication industry is in need to do that, because as much as we are speaking about edge data centers, that means that we will need also to have, I would say, the connectivity and the right connectivity going to those edge data centers, because collecting data at the edge and processing data at the edge means also having a very good network in terms of latency and in terms also of energy consumption. And today, what is hurting the telco is basically their data centers and the energy consumption within their communication centers. So telecommunication is definitely one of our markets.
If I could comment also, we view telcos as there's two issues. One is at the data center itself, and then the other is at the edges, was Serge just mentioned. We actually make a product called the mini node, which is the size of a boot box that can fit on a street lamp. And so we recognize that latency is a big issue, increasingly large issue, as with 5 and 6G. And so you could have a node at a boot box size at a street lamp on the corner. We also have, because all we need is connectivity and power, we can literally locate our servers anywhere, even outside, in any weather. They, of course, have to be weatherized for rain or snow, but they're completely flexible. So it provides an interesting leap for these telcos to completely change the way they currently manage their computing activity and connectivity.
Right, perfect. Thanks. Oh yeah, there's another question for me. So how big in average is the thermal interface material? What thickness is normally used in liquid cooling? So regarding the size of the thermal interface material for server boards, essentially it largely depends on like how big your server board is or how big your chipset is. So it could really range from, so for example, for a chip with a size of, let's say, like 14 centimeter square, then you're essentially looking at a team gap pad around a similar size. So in terms of the thickness of teams in liquid cooling, so again, this depends on what sort of like a team you're using. So if you're using thermal grades, then you can be looking at somewhere between, let's say 200 micrometers up to 1,000 micrometers. So that is the typical thickness of the team for the specific applications. But again, if you're talking about graphite, then the thickness could vary, and I can't really remember the thickness off the top of my head. But hopefully, this is the sort of like a general ballpark figure for this question. I'm not sure whether any of you guys has any comments on the thermal interface materials or not. No?
Well, if you deal with immersive cooling on our side, we are completely removing the teams, and also our side we are completely cleaning, I will say, the heat paste, okay, which is between the heat exchanger and the processor itself. We don't use anything. We have been tested, I would say, some graphene layer in order to increase, I would say, the thermal conductivity between the processor itself and the heat exchanger, but that we don't have any gain outside of it. So outside of maybe potentially on the Intel chipset, avoiding the liquid to go on the little hole which is on the top of the processor, that's basically the only benefit we haven't seen. But on the thermal side, because of maybe the way we have our liquid circulating, because maybe the kind of the liquid that we are using, we don't have any use of TEAM. Maybe Matt, you have another experience, or
I mean, we've done some of quite a bit of it from retrofitting servers a few years ago, before there was so much availability, and lead more towards, so it's definitely removing all of the thermal paste and then replacing either indium foil as an interface with the heat sinks, or when you're looking at some of the, and this is third hand for me, it says I know what was done by TCRSI who did the work for us. When it comes to the GPUs, where it's really replacing thermal blocks, where there is a varying gap between their heat sink within the GPU, and replacing that with more. Now, some people are using that with a custom design heat sink. Some are using blocks to use a generic heat sink, but yeah, we don't use any thermal paste across our immersed portfolio because we found it just dissolved, basically.
Well, that's our experience too. The greases and pastes, they basically absorbed in the fluid and they muck up everything. We use an indium film right now. There is a lot of work being done on these thermal interface materials, and we're hopeful that we can get better thermal connectivity at the processor level. But right now, we pretty much do what everybody else does, because the greases and paint and paste do end up in the fluid and are a problem. So,
right. So there's a question for Serge and Herb. Can you talk about the difference in terms of cost, time, and practicality between retrofitting existing data centers with your tech versus using it in new data centers?
I can go first, I suppose.
Okay.
First of all, because the introduction of the liquid cooling loop that has to be built in every data center going forward in order to accommodate high power processors, it's become quite easy. The hurdle used to be getting data center operators to accept liquids in the white space. Well, that's come and gone. That problem's been solved. And so now it's simply a matter of either retrofitting or building a new facility with that loop in place. And once that's done, the game is over. I mean, air cooling never made sense in my mind, and increasingly will become out of gone. It'll be in the rearview mirror pretty soon. So then the question becomes, what kind of liquid cooling do you go for? There's all kinds of choices. My personal view, but I have a dog in the fight, is that direct-to-chip is a transition technology that's leading to immersion. And once the immersion takes over, then the question becomes, how do you cool the hot chips? And my view is you need some kind of forced convection there. And then nature will take its course. It's less expensive, actually, to migrate from air to liquid using a normal refresh once that loop is involved, and to continue buying air servers. Serge, you have a thought?
Well, I can say I completely agree with what you said in terms of I think we're gonna be in a period where DLC and immersive cooling, okay, are gonna be basically cohabitating, okay, within the same data center or within the same data. We are basically, and when we talk about the retrofitting existing data center, let's be clear on the word: is a retrofitting or it is a migration, okay? Because if it's a migration, don't forget that the room which are already installed on air-cooled, people are never going to remove their appliances to move to immersive cooling. No, it's going to be the next generation, the next data room, who's going to be immersive cooling compliant. And then in this immersive cooling room, you will see DLC, okay, and you will see immersive cooling. I'm pretty sure I would say the two are going to be cohabitating together. So then after that, the cost of it, well, all depends if you buy it or if you rent it. But in terms of the physical infrastructures, like I would say for DLC, you're gonna have basically, I would say, the 6 centimeters, cool loop within the room, and you will be basically connecting, I would say, your system one after another based on the demand. So that's basically the way I see it. Now, the thing that's going to be changing is the quality of the materials. One thing is important when you speak about corrosion, oxidation, whiskers, dust, electrostatic, all of those with immersive coolings are gone. Okay, and that's the beauty of the immersive cooling, basically solving what electronics lifespan has been suffering, called the MTBF, which is mechanical vibration, which are the fans, and also the temperature swing, fast temperature swing, which electronic doesn't like. So when you solve all those problems there, then basically it's all about the quality of the electronics that you guys are going to be using. We're going to be basically lasting as long as they are not becoming obsolete, as long as you write the code in order to optimize CPUs and memories, and as long as I said the electronic itself will last. But within the liquid, basically you solve all problems in terms of waste, in terms of longevity, and in terms of external phenomena. Basically, you arrive to a system which is completely agnostic, and you can immerse it. Matt?
Just one more comment on that.
Yeah, I was going to say, yeah, from a deployment, speaking a bit, we've touched a lot on the benefits. I think on the practicality perspective, it's slightly more nuanced. I think it's more a possibility where you look at particularly elements like floor loading. When if you're retrofitting existing space, you've either got a facility that is able to accommodate or not. Now, that, as Serge touched on, there are going to be a lot of legacy air-cooled systems that are just going to sat there where the structural upgrades and the upgrades to put in the loops, as Herb spoke about, are just not viable for that space. So it's better to wait to end of life and then fully upgrade the facility. But I think if we're assuming, I think it's a fair assumption that densities are going to continue getting higher from a power perspective, that as a result, a lot of the servers are going to get heavier. Because even if you look at NVIDIA's most recent launch, that was, now correct me if I'm wrong, Serge, but that was coming in at a higher loading weight than any of the solutions we're looking at here. I know, kind of weight per square meter. So if we're assuming from that perspective, the installation is not hard at all. And the payback period, where you look at the simplicity of operations, the reduced maintenance workload, the reduced cooling power consumption, is very, very quick. I think what it fundamentally comes down to is potentially a slight change in the way we're charging within the data center space, because you are talking about what is not with immersion 4, but in general, a slightly higher capital outlay up front on a per kilowatt basis that needs to be recovered in some way. And that will, I think, the way we're approaching it is that's being bundled into your reserve power fee. It's just a slight change of way of thinking it, from chuck £2,500 or £10,000 up front as installation costs and making the client pay for it on the install, which some people do now, to absorbing that fully within the CapEx or adopting an OpEx solution like immersion 4 do, so that you can pass that cost on to the client in a way that they're seeing the benefits and you're also seeing the business case.
Yeah. Great. Thanks, Matt. Yeah, I think we are running out of time. I do see there are still quite a few questions in the chat. So, for those people whose questions didn't get answered, please do feel free to sort of like a follow up with relevant people. I'm pretty sure those guys are very happy to talk about the things. Yeah, so please do feel free to email them or myself or Peter, and I'm sure we can follow up on that. So in the interest of time, I will hand the stage back to Peter.
Okay. Thank you so much, Matt, Herb, Serge, and Yulin for sharing your insights. Yulin for leading the discussion. Also, thank you to everyone listening in today and posting questions. Personally, I would have liked to learn a little bit more about the possible role of ceramic ultra wideband semiconductor materials in solving the thermal challenges in data centers, but we'll leave that for the conference. That one is coming up April 30, May 1 in Novi, Michigan, the Thermal Management and Ceramics Expos there. So go to the website and sign up there. The session has been recorded and will be made available to watch on demand, also on the website. Just look for webinars, click on it, and you should be able to see the webinars eventually. So thank you again. Thanks to everybody who participated, and have an excellent rest of the day.
Thank you. Nice to see you, gentlemen. Thanks for everyone.
So,